Welcome to this presentation on dynamic matrix control. We will recall some basics from discrete time control. We will derive the system matrix for DMC, dynamic matrix control, and we will also arrive at the control law. Now let us get the plant output as a function of step input. Recall our convolution expression. The plant output Yn is given by the impulse response G convolved with plant input U. Of course, we have taken the plant as LTI system at 0 initial state. Recall the expression for impulse as a function of unit step, and hence the impulse response as a function of step response, the difference in step response, which we can denote as delta of Sn. When I substitute the expression for G as delta Sn here, I get this expression, and we can show that I can shift this delta over here. It is easy to see this if you look at it in Z transform. This is the expression we arrived at in the previous slide. This is the output due only to the control effort U. That is, the above is really Y sub U, because we have taken Yx to be equal to 0, that is 0 initial state in the input output setting. If Yx is not equal to 0, we have to add that also. So we need to add this Y sub x, and this whole thing is Y sub U. So when I substitute Yx is here, for Yu I substitute here, I get this convolution expression. This is the sum of output due to non-zero initial condition only, which is the first term, and output due to input only, which is this term. Now we will use this expression. So let us call it Y hat. Instead of writing it as Y, we will write it as Y hat, and we will start with k plus 1. The current time instant is k, so we are predicting the plant output at the next time instant Y of k plus 1. Because it is estimate, we put a hat here. In the place of this convolution, I have written this. We have to write all terms such that the sum of these two indexes k and 1 should be equal to k plus 1. Here k plus 1 is equal to, if I add this k and 1, I get this k plus 1. In fact, we have to consider all such terms. I have introduced a term called B. So we have taken S of 0 equals 0. That is because we expect at least one delay in sampled data systems. I have not explained what B is. It is called a bias. It is supposed to take care of modeling errors, noise, etc. We will shortly explain how to estimate this B. Let me write the same expression for k plus 2 now. Only in the case of convolution you have an extra term, because k plus 1 and 1 is k plus 2, k and 2 is k plus 2, and S of 0 is already 0, so we do not have to consider that term. B of k plus 2 is not known yet. So let me continue this and go all the way up to Nu plus 1, where Nu is the control horizon. It has terms up to k plus Nu, delta U of k plus Nu, starting from delta U of k, k plus 1, k plus 2 and so on, all the way up to delta U of k plus Nu. So what is the reason to write this? We will see it in the next slide. Okay, this is the expression we arrived at in the previous slide. Now because Nu is the control horizon, we apply the control effort up to K plus Nu only and keep it constant afterwards. That is delta U of K plus M equals 0 for all M greater than Nu. That is delta U of K plus Nu plus 1 equals 0, K plus Nu plus 2 equals 0 and so on. That is all subsequent intervals this delta U terms will be 0. That is because the control effort has become constant at Nu. So when I write it for the next time instant, I go up to K plus Nu only, because the next term is K plus Nu plus 1 multiplying S of 1, but that is K plus Nu plus 1, which is 0, so I do not have to write it. All other terms are same as before. Okay, this is what we had in the previous slide. Continue with this and go all the way up to K plus N. N is the prediction horizon and N is greater than Nu in general. We stack these up, we get an expression of this type. The first term has all the y sub x, the second term has all the delta U terms, and this vector B term has all the bias entries in every equation. We will see the expression for S underscore in the next slide. Here is the expression for S underscore. This consists of step response terms S1, S2 and so on. So this matrix S underscore has n rows, you can see 1 through n, and Nu plus 1 columns. You can see here 1 through Nu plus 1. And because of the condition that delta U becomes 0 after Nu, you do not have subsequent terms. As a result, this is a tall matrix. So this is the expression we arrived at 2 slides ago. We saw the value of S underscore in the previous slide. The other variables are given here. Y hat of K plus 1 is given here, and here is Y underscore X, U underscore K. It consists of all delta U terms and B underscore terms. I have an assignment for you. Develop the system matrix for n equals 5, that is the prediction horizon, and control horizon Nu equals 3. Now let us solve the DMC model. Here is the reference signal. Now let us force the plant output to be equal to the reference signal. I get this expression. This is what we had in the previous slide. This was equal to Y hat. Now let us rearrange the terms. I have taken the R underscore term to the right hand side and equated to 0 to get this expression. So I have this minus R here and minus plus here. Similarly, this is going to be plus. Let us define the terms within the square brackets as E underscore. So I get this equation. And because this is a tall matrix, it does not have an exact solution. We can only get least squares minimization. So here is the least squares solution. It is given by the standard expression. Here is the DMC control law. To prevent excessive control action, we weight the control effort also. That is, we include a term of this type, rho squared times I. This is similar to the GPC case. We explained in the previous video, when we derived the GPC law, how this expression comes about. Alright, now we will talk about the calculation of the bias term B, which we postponed previously. This is how we introduce the bias term. So, I will write B as y hat k minus this whole thing. Now, we will estimate this B from the most recent measurement. Remember, the current time instant is k. We have just measured the plant output y of k, and we have to implement the control effort from delta u k onwards. We have just done the measurement, we have to implement the control law. That is where we are. So, what we will do is we will estimate this y hat of k as y of k, and then we will subtract this yxk plus yu of k. So, this is the bias term. It is obtained from this expression by replacing y hat with y. We will also assume that the bias is constant, that is b of k plus 1 is equal to b of k. Remember that we need the bias term for all subsequent intervals. So, we will let b of k plus 1 equals b of k plus 2 equals b of k, and so on. All future bias terms are let equal to b of k, that is constant. So, this is nothing but a crude modeling of noise. We have not actually written detailed noise models as we did in GPC law, but this is lot easier to explain, lot easier to implement. Although it is approximate, it works. As in GPC law, we will use receding horizon control approach. We will implement only the first control move. We will calculate the control law afresh at every interval. The range of values over which we do the minimization also keeps shifting. So, this is known as the receding horizon control. We will calculate the bias term for every interval using the latest measured y value. To conclude, DMC is based on step response coefficients, which can be determined from identification either directly or through impulse response coefficients. We saw this in one of the earlier weeks where we described the identification method. We use receding horizon method in MPC, model predictive control. In DMC also we use receding horizon control, wherein we calculate the bias term for every move. The control law is calculated for every move. Only one control move is implemented, however. The noise model is very crude, but it is easy to implement. There is no complicated modeling. It works reasonably well. This brings us to the end of this presentation, not only for this presentation, but also for the lectures in this week. I would want you to try out the methods given here. I would want you to work out the expressions. I would want you to use the Scilab code and validate your understanding. Thanks for joining. Goodbye.